to our next talk. It's called Flipping Bits from Software Without Rowhammer. Small reminder, Rowhammer it still is a software-based fault attack. It was published in 2015. There were countermeasures developed, and we are still in the process of deploying these everywhere. And now our two speakers are going to talk about a new software-based fault attack to execute commands inside the SGX environment. Our speakers, Professor Daniel Gruß from the University of Graz, and Kit Murdoch, researching at the University of Birmingham. The content of this talk is actually in her first published paper, published at accepted at IEEE Security and Privacy next year. In case you do not come from the academic world, if this is this always is a big deal. And if this is your first paper, it even more is. Please welcome them both with a huge round of applause and enjoy the talk.
Thank you. Hello. Let's get started. This is my favorite recent attack. It's called Clockscrew. And the reason that it's my favorite is it created a new class of fault attacks.
Fault attacks, I know that. Fault attacks, you take these oscilloscopes and check the voltage line, and then you drop the voltage for...
No, you see, this is why this one is cool, because you don't need any equipment at all. Oh. Adrian Tang, he created this wonderful attack that uses DVFS. What's that?
DVFS? I don't know. Don't violate format specifications?
I asked my boyfriend this morning what he thought DVFS stood for, and he said, Darth Vader fights Skywalker. And I'm also wearing his T-shirt specially for him as well.
Maybe this is more technical. Maybe dazzling vault for security, like SGX?
No, it's not that either. Mine was, the one I came up this morning was drink vodka, feel silly. It's not that either. It stands for dynamic voltage and frequency scaling. And what that means, really simply, is changing the voltage and changing the frequency of your CPU. Why do you want to do this? Why would anyone want to do this? Well, gamers want fast computers. I am sure there are a few people out here who will want a really fast computer. Cloud servers want high assurance and low running costs. And what do you do if your hardware gets hot? You're going to need to modify them. And actually finding a voltage and frequency that work together is pretty difficult. And so what the manufacturers have done to make this easier is they've created a way to do this from software. They created memory-mapped registers. You modify this from software, and it has an impact on the hardware. And that's what this wonderful Clockscrew attack did. But they found something else out, which is, you may have heard of TrustZone. TrustZone is an enclave in ARM chips that should be able to protect your data. But if you can modify the frequency and voltage of the whole core, then you can modify it for both TrustZone and normal code. And this was their attack. In software, they modified the frequency to make it outside of the normal operating range, and they induced faults. And so in an ARM chip running on a mobile phone, they managed to get out an AES key from within TrustZone. They should not be able to do that. They were able to trick TrustZone into loading a self-signed app. You should not be able to do that. And that made this ARM attack really interesting. This year, another attack came out called Volt Jockey. And this also attacked ARM chips, but instead of looking at frequency on ARM chips, they were looking at voltage on ARM chips. We're thinking, what about Intel?
OK, so Intel, actually I know something about Intel, because I had this nice laptop from HP. I really liked it, but it had this problem that it was going too hot all the time, and I couldn't even work without shutting down all the time because of the heat problem. So what I did was I undervolted the CPU, and actually this worked for me for several years. I used this undervolted for several years. You can also see this. I just took this from somewhere on the internet, and they compared with undervolting and without undervolting, and you can see that the benchmark score improves by undervolting because you don't run into the thermal throttling that often. So there are different tools to do that. On Linux or on Windows, you could use RM clock. There's also throttle stop. On Linux, there's the Linux Intel Undervolt GitHub repository.
And there's one more, actually. Adrian Tang, who I don't know if you know, I'm a bit of a fan. He was the lead author on Clockscrew. He wrote his PhD thesis. And in the appendix, he talked about undervolting on Intel machines and how you do it. And I wish I'd read that before I started the paper. That would have saved me an awful lot of time. But thank you to the people on the internet for making my life a lot easier, because what we discovered was there is this magic model-specific register. Ooh, and it's called Hex 150. And this enables you to change the voltage. The people on the internet did the work for me, so I know how it works. You first of all tell it, the plain IDX, what it is you want to raise the voltage or lower the voltage. We discovered that the core and the cache are on the same plane, so you have to modify them both, but it has no effect. They're together. I guess in the future they'll be separate. And then you modify the offset to say, I want to raise it by this much or lower it by this much. So I thought, let's have a go. Let's write a little bit of code. Here is the code. The smart people amongst you may have noticed something. I suspect even my appalling C, even I would recognize that that loop should never exit. I'm just multiplying the same thing again and again and again and again and again and expecting it to exit. That shouldn't happen. But let's look at what happened. So I'm going to show you what I did. Oh, ooh. There we go. So the first thing I'm going to do is I'm going to set the frequency to be one thing, because I'm going to play with voltage. And if I'm going to play with voltage, I want the frequency to be set. So it's quite easy using CPU power. You set the maximum and the minimum to be 1 gigahertz, and now my machine is running at exactly 1 gigahertz. Now we'll look at the bit of code that you need to undervolt. Again, I didn't do the work. Thank you to the people on the internet for doing this. You put the MSR into the kernel, and let's have a look at the code. Does that look all right? Oh, it does. Looks much better up there. Yes, it's that one line of code. That is the one line of code you need to open, and then we're going to write to it. And again, oh, why is it doing that? We have a touch-sensitive screen here. I won't touch it again. That's the line of code that's going to open it, and that's how you write to it. And again, the people on the internet did the work for me and told me how I had to write that. So what we're going to do here is I'm just going to undervolt. And I'm going to undervolt multiplying dead beef by this really big number. I'm starting at minus 252 millivolts, and we're just going to see if I ever get out of this loop.
But surely the system would just crash, right?
You'd hope so, wouldn't you? Let's see. There we go. We got a fault. I was a bit gobsmacked when that happened, because the system didn't crash.
So that doesn't look too good. So the question now is, what is the, so you show some voltage here, some undervolting, 0?
Yeah.
What undervolting is actually required to get a bit flip?
Well, we did a lot of tests. We didn't just multiply by dead beef. We also multiplied by random numbers. So here I'm going to just generate 2 random numbers. One is going up to FFFFFF, and one is going up to FFF. And I'm just going to try different, again, I'm going to try undervolting to see if I get different bit flips. And again, I got the same bit flip, so I'm getting the same one single bit flip there. OK, so maybe it's only ever going to be one bit flip. Ah, I got a different bit flip. And again, a different bit flip. And it's you'll notice there always appear to be bits together next to one another. So to answer Daniel's question, I crashed my machine a lot in the process of doing this. But I wanted to know what were good values to undervolt at. And here they are. We tried for all the frequencies. We tried what was the base voltage, and then when was the point at which we got the first fault. And once we'd done that, it made everything really easy. We just made sure we didn't go under that and ended up with a kernel panic or the machine crashing.
So this is already great, and I think so. This looks like it is exploitable. And the first thing that you need when you are working on a vulnerability is the name and the logo and maybe a website, everything like that. And really, people on the internet agree with me, like this tweet. Yes. So we need a name and a logo.
We don't need to. Go on then. Go on then. What's your idea?
So I thought this is like, it's like Rowhammer. We are flipping bits, but with voltage. So I call it Volthammer. And I already have a logo for it.
We're not giving it a logo.
No, I think we need a logo because people can relate more to the images there, to the logo that we have. Reading a word is much more complicated than seeing a logo somewhere. It's better for communication. You make it easier to talk about your vulnerability. Yeah? And the name, same thing. How would you like to call it? Like undervolting on Intel to induce flips in multiplications to then run an exploit? No, that's not a good vulnerability name. And speaking of the name, if we choose a fancy name, we might even make it into TV shows like Rowhammer.
The hacker used a DRAM Rowhammer exploit to gain kernel privileges.
Hey, Chuck. Yeah, I've got something for you.
So this was in Designated Survivor in March 2018, and this guy just got shot. So hopefully we won't get shot, but actually we have also been working, so my group has been working on Rowhammer and presented this in 2015 here at CCC, in Hamburg back then. And it was Rowhammer JS, and we called it root privileges for web apps because we showed that you can do this from JavaScript in a browser. Looks pretty much like this. We hammer the memory a bit, and then we see bit flips in the memory. So how does this work? Because maybe for another fault attack, software-based fault attack, the only other software-based fault attack that we know. So these are related to DVFS, and this is a different effect. So what we do here is we look at the DRAM, and the DRAM is organized in multiple rows. And we will access these rows. These rows consist of so-called cells, which are capacitors and transistors each, and they store 1 bit of information each. And the row buffer, the row size, usually is something like 8 kilobytes, and then when you read something, you copy it to the row buffer. So it works pretty much like this. You read from a row, you copy it to the row buffer. The problem now is these capacitors leak over time, so you need to refresh them frequently. And they have also a maximum refresh interval defined in a standard to guarantee data integrity. Now, the problem is that cells leak fast upon proximate accesses. And that means if you access 2 locations in proximity to a third location, then the third location might flip a bit without accessing it. And this has been exploited in different exploits. So the usual strategies, maybe we can use some of them. So the usual strategies here are searching for a page with a bit flip. So you search for it, then you find some, there's a flip here. Then you release the page with the flip in the next step. Now this memory is free. And now you allocate a lot of target pages, for instance, page tables. And then you hope that the target page is placed there. If it's a page table, for instance, like this, and you induce a bit flip, so before it was pointing to user page, then it was pointing to no page at all because we maybe unmapped it. And the page that we induced the bit flip now is actually the one storing all the PTEs here. So the one in the middle, stored down there. And this one now has a bit flip, and then our pointer to our own user page changes due to the bit flip and points to, hopefully, another page table because we filled the memory with page tables. Another direction that we could go here is flipping bits in code. For instance, if you think about a password comparison, you might have a jump equal check here. And the jump equal check, if you flip 1 bit, it transforms into a different instruction. And fortunately, oh, this already looks interesting. Ah, perfect. Changing the password check into a password incorrect check. I will always be root. Yeah, that's basically it. So these are two directions that we might look at. For Rowhammer, that's also maybe a question. For Rowhammer, why would we even care about other fault attacks? Because Rowhammer works on DDR3, it works on DDR4, it works on ECC memory.
How does it deal with SGX?
Yeah, SGX. Yes. So maybe we should first explain what SGX is.
Go for it.
SGX is a so-called TE, Trusted Execution Environment, on Intel processors. And Intel designed it this way that you have an untrusted part, and this runs on top of an operating system inside an application. And inside the application, you can now create an enclave. And the enclave runs in a trusted part, which is supported by the hardware. The hardware is the trust anchor for this trusted enclave. And the enclave, now you can, from the untrusted part, you can call into the enclave via a call gate, pretty much like a system call. And in there, you execute a trusted function. Then you return to this untrusted part, and then you can continue doing other stuff. And the operating system has no direct access to this trusted part. This is also protected against all kinds of other attacks, for instance, physical attacks. If you look at the memory that it uses, maybe I have 16 gigabytes of RAM, then there is a small region for the EPC, the enclave page cache, the memory that enclaves use. And it's encrypted and integrity protected, and I can't tamper with it. So for instance, if I want to mount a cold boot attack, pull out the DRAM, put it in another machine, and read out what content it has. I can't do that because it's encrypted and I don't have the key. The key is in the processor. Quite bad. So what happens if we have bit flips in the EPC? Good question. We tried that. The integrity check fails. It locks up the memory controller, which means no further memory accesses whatsoever run through this system. Everything stays where it is, and the system halts, basically. It's no exploit, it's just denial of service.
Ah, so maybe XGX can save us. So what I want to know is, Rowhammer clearly failed because of the integrity check. Is my attack, where I can flip bits, is this going to work inside SGX?
I don't think so, because they have the integrity protection, right?
So what I'm going to do is run the same thing. In the right-hand side is user space, and in the left-hand side is the enclave. As you can see, I'm running it at minus 261 millivolts, no error. Minus 262, no error. Minus 2. Fingers crossed we don't get a kernel panic. Do you see that thing at the bottom?
Ooh.
That's a bit flip inside the enclave. Oh, yeah.
That's bad.
Thank you. Yeah. And it's the same bit flip that I was getting in user space. That is also really interesting.
I have an idea. So it's surprising that it works, right? But I have an idea. This is basically doing the same thing as Clockscrew, but on SGX, right?
Yeah.
And I thought maybe you didn't like the previous logo. Maybe it was just too much. So I came up with something more simple.
He's come up with a new name.
SGX Screw. How do you like it?
No. We don't even have an attack. We can't have a logo before we have an attack.
But the logo is important, right? I mean, how would you present this on a website without a logo?
Well, first of all, I need an attack. What am I going to attack with this?
I have an idea what we could attack. So, for instance, we could attack crypto. RSA. RSA is a crypto algorithm. It's a public key crypto algorithm. And you can encrypt or sign messages. You can send this over an untrusted channel, and then you can also verify. So this is actually a typo. It should be decrypt there. Encrypt, verify messages with a public key, or decrypt sign messages with a private key. So how does this work? Basically it's based on exponentiation modulo a number, and this number is computed from 2 prime numbers. So for the signature part, which is similar to the decryption basically, you take the hash of the message and then take it to the power of d modulo n, the public modulus, and then you have the signature. And everyone can verify that, that this is actually, later on can verify this, because the exponent part is public. So n is also public, so we can later on do this. Now, there is one optimization which is quite nice, which is Chinese remainder theorem. And this part is really expensive. It takes a long time. So it's a lot faster if you split this in multiple parts. For instance, if you split it in 2 parts, you do 2 of those exponentiations, but with different numbers, with smaller numbers, and then it's cheaper. It takes fewer rounds. And if you do that, you, of course, have to adapt the formula up here to compute the signature, because you now put it together out of the 2 pieces of the signature that you compute. OK, so this looks quite complicated. But the point is, we want to mount a fault attack on this. So what happens if we fault this? Let's assume we have 2 signatures which are not identical, right? S and S prime. And we basically only need to know that in one of them a fault occurred. So the first is something, the other is something else. We don't care. But what you see here is that both are multiplied by q plus S2. And if you subtract one from the other, what do you get? You get something multiplied with q. There's something else that is multiplied with q, which is p. And n is public. So what we can do now is we can compute the greatest common divisor of this and n and get q.
OK, so I'm interested to see if I didn't understand a word of that, but I'm interested to see if I can use this to mount an attack. So how am I going to do this? Well, I'll write a little RSA decrypt program. And what I'll do is I'll use the same bit of multiplication that I've been using before. And when I get a bit flip, then I'll do the decryption. All this is happening inside SGX, inside the enclave. So let's have a look at this. First of all, I'll show you the code that I wrote. Again, copied from the internet. Thank you. So there it is. I'm going to trigger the fault. I'm going to wait for the trigger of fault. Then I'm going to do a decryption. And let's have a quick look at the code, which should be exactly the same as it was right at the very beginning when we started this. Yeah, there's my dead beef. It's written slightly differently, but there's my dead beef. So now this is ever so slightly messy on the screen, but I hope you're going to see this. So minus 239, fine. Still fine. Still fine. I'll just pause there. You can see at the bottom I've written meh, all fine, if you're wondering. So what we're looking at here is a correct decryption. And you can see inside the enclave, I'm initializing P and I'm initializing Q. And those are part of the private key. I shouldn't be able to get those. So 239 isn't really working. Let's try going up to minus 240. RSA error, RSA error. Exciting.
OK, so this should work for the attack then.
So let's have a look. Again, I copied somebody's attack on the internet, where they very kindly, it's called the Lenstra attack. And again, I got an output. I don't know what it is, because I didn't understand any of that crypto stuff. But let me have a look in the source code and see if that exists anywhere in the source code inside the enclave. It does. I found P. And if I found P, I can find Q. So just to summarize what I've done, from a bit flip, I have got the private key out of the SGX enclave. And I shouldn't be able to do that.
Yes, yes. And I think I have an idea. So you didn't like the previous...
I know where this is going. Yes.
Didn't like the previous name. So I came up with something more cute and relatable, maybe. So I thought, this is an attack on RSA. So I called it Mufasa. My undervolting fault attack on RSA.
That's not even a logo. That's just a picture of a lion.
Yeah, it's sort of.
Disney aren't going to let us use that. Oh, it's not. Is it Star Wars now? I don't know. OK. OK. So, Daniel, I really enjoyed...
I don't think you will like any of the names I suggest,
probably
right?
not. But I really enjoyed breaking RSA. So what I want to know is, what else can I break? Give me something else I can break.
If you don't like the RSA part, we can also attack other crypto. I mean, there's AES, for instance. AES is a symmetric key crypto algorithm. Again, you encrypt messages, you transfer them over a public channel, this time with both sides having the key. You can also use that for storage. AES internally uses a 4x4 state matrix for 4x4 bytes. And it runs through 10 rounds, which are S-blocks, which basically replaces a byte by another byte. Some shifting of rows in this matrix, some mixing of the columns, and then the round key is added, which is computed from the AES key that you provide to the algorithm. And if we look at the last 3 rounds, because we want to, again, mount a fault attack, and there are different differential fault attacks on AES. If you look at the last rounds, because the way of this algorithm works is it propagates changes, differences, through this algorithm. If you look at the state matrix, which only has a difference in the top left corner, then this is how the state will propagate through the 9th and 10th round, and you can put up formulas to compute possible values for the state up there. If you have if you have encryptions which only have a difference there in exactly that single state byte. Now, how does this work in practice? Well, today everyone is using AES-NI because that's super fast. That's again, an instruction set extension by Intel, and it's super fast.
Oh, OK. I want to have a go. Right, so let me have a look if I can break some of these AES new instructions. So I'm going to come at this slightly differently. Last time I waited for a multiplication fault. I'm going to do something slightly different. What I'm going to do is put in a loop 2 AES encryptions, and I wrote this using Intel's code. I should say we wrote this using Intel's code, example code. This should never fault. And we know what we're looking for. What we're looking for is a fault in the 8th round. So let's see if we get faults with this. So the first thing is, I'm going to start at -262 millivolts. What's interesting is that you have to undervolt more when it's cold. So you can tell at what time of day I ran these. Ah, I got fault. Oh, unfortunately, where did that? That's actually in the 4th round. I'm obviously, oh, 5th round?
You can't do anything with that.
You can't do anything. Again, in the 5th round, can't do anything with that. 5th round again. Oh, we got one. We got one in the 8th round. And so it means I can take these 2 ciphertexts, and I can use the differential fault attack. I actually ran this twice in order to get 2 pairs of faulty output, because it made it so much easier. And again, thank you to somebody on the internet for having written a differential fault analysis attack for me. You don't need 2, but it just makes it easy for the presentation. So I'm now going to compare. Let me just pause there a second. I used somebody else's differential fault attack, and it gave me, for the first pair, it gave me 500 keys, possible keys, and for the second, it gave me 200 possible keys. I'm overlapping them, and there was only 1 key that matched both, and that's the key that came out. And let's just again check inside the source code, does that key exist? What is the key? And yeah, that is the key. So again,
that's not a very good key, though.
No. I think if you think about randomness, it's as good as any other. Anyway, what have I done? I have flipped a bit inside SGX to create a fault in AES new instruction set that has enabled me to get the AES key out of SGX. I shouldn't be able to do that.
So now that we have multiple attacks, we should think about a logo and a name, right?
This one better be good, because the other one wasn't very good.
No, seriously, we are already soon. We will write this up, send this to a conference. People will like it, right? And I already have a name and a logo for it.
Come on then.
Cryptovolt screw hammer. It's like we attack crypto in a vault, SGX, and it's like like the Clockscrew and like Rowhammer and like.
I don't think that's very catchy. But let me tell you, it's not just crypto. So we're faulting multiplications. So surely there's another use for this other than crypto. And this is where something really interesting happens. For those of you who are really good at C, you can come and explain this to me later. This is a really simple bit of C. All I'm doing is getting an offset of an array and taking the address of that and putting it into a pointer. Why is this interesting? It's interesting because I want to know what the compiler does with that. So I'm going to wave my magic wand. And what the compiler's going to do is it's going to make this. Why is that interesting?
Simple pointer arithmetic.
Well, we know that we can fault multiplications. So we're no longer looking at crypto. We're now looking at just memory. So let's see if I can use this as an attack. So let me try and explain what's going on here. On the right-hand side, you can see the undervolting. I'm going to create an enclave, and I've put it in debug mode so that I can see what's going on. You can see the size of the enclave because we've got the base and the limit of it. And if we look at that in a diagram, what that's saying is, here, if I can write anything at the top above that, that will no longer be encrypted. That will be unencrypted. OK, let's carry on with that. So let's just write that one statement again and again, that pointer arithmetic again and again and again whilst I'm undervolting, and see what happens. Oh, suddenly it changed. And if you look at where it's mapped it to, it's mapped that pointer to memory that is no longer inside SGX. It's put it into untrusted memory. So we're just doing the same statement again and again whilst undervolting. Bish, we've written something that was in the enclave out of the enclave. And I'm just going to display the page of memory that we've got there to show you what it was. And there's the one line. It's dead beef. And again, I'm just going to look in my source code to see what it was. Yeah, it's, you know, endian this, blah, blah, blah. I have now not even used crypto. I have purely used pointer arithmetic to take something that was stored inside Intel's SGX and moved it into user space where anyone can read it.
So yes, I get your point. It's more than just crypto, right?
Yeah.
It's way beyond that. So we leaked RSA keys. We leaked AES keys.
Yeah, we did not just that, though. We did memory corruption. OK. So yeah, OK. Cryptovolt Screwhammer, point taken, is not the ideal name. But maybe you could come up with something. We need a name and a logo. OK, pressure's on me then. Right, here we go. So it's got to be due to undervolting, because we're undervolting. Maybe we can get a pun on volt and volt in there somewhere. We're stealing something, aren't we? We're corrupting something. Maybe we're plundering something.
Yeah?
I know.
Yeah?
Let's call it Plundervolt.
Oh, no. That's not a good name.
What?
No, we need something. This is really not a good name. People will hate this name. Wait. No.
You can read this if you like, Daniel.
OK, I think I get it. I think I get it.
No, I haven't finished.
OK. Yeah, this is really also a very nice comment. Yes, the quality of the videos. I think you did a very good job there.
Thank you.
Also, the website, really good job
there. So just to summarize, what we've done with Plundervolt is it's a new type of attack. It breaks the integrity of SGX. It's within SGX, we're doing stuff we shouldn't be able to.
Like AES keys. We leak AES keys, yeah?
And we are retrieving the RSA signature key.
Yeah. And yes, we induced memory corruption in bug-free code.
And we made the Enclave write secrets to untrusted memory. This is the paper that's been accepted next year. It is my first paper, so thank you very much. Kit, that's me. Thank you. David Oswald, Flavio Garcia, Johan Bolk, and of course, the infamous, and Frank Pearson. So all that really remains for me to do is to say thank you very much for coming.
Wait a second. There's one more thing. I think you overlooked one of the tweets. I added it here. You didn't see this slide yet.
I haven't seen this one.
I really like it.
It's a slightly ponderous pun on Thunderbolt. Pirate-themed logo.
A pirate-themed logo. I really like it. And if it's a pirate-themed logo, don't you think there should be a pirate-themed song?
Daniel, have you written a pirate-themed song? Go on then, play it. Let's hear the pirate-themed song.
Yo ho, some undervolt for me. We pillage, we plunder TES, root, pull down, the Enclaves, yo ho. We fault the encryption and often reboot, pull down, the Enclaves, yo ho. Yo ho, some undervolt for me. We fault the signature, then we crack, pull down, the Enclaves, yo ho. RSA we face a little backdoor attack, pull down, the Enclaves, yo ho. Yo ho, some undervolt for me. We fiddle and try AES-NI, pull down, the Enclaves, yo ho. We just take a minute to get the key by, pull down the Enclaves, yo ho. We know you believe that memory's safe, pull down the Enclaves, yo ho. We flip allocations of the Enclave, pull down the Enclaves, yo ho. Yo ho, some undervolt for me. We propose security SGA stack, pull down the Enclaves, yo ho. I got his fix with a microcode patch, pull down the Enclaves, yo ho.
Thanks to Thanks to Manuel Weber and also to my group at TU Graz for volunteering for the choir. And then, I mean, this is now the last slide. Thank you for your attention. Thank you for being here. And we would like to answer questions in the Q&A.
Thank you for a great talk. And thank you some more for the song. All right, if you have questions, please line up on the microphones in the room. First question goes to the Signal Angel. Any question from the internet?
Not as of now, no.
All right, then microphone number 4, your question, please.
Hi, thanks for the great talk. So why does this happen now? I mean, thanks for the explanation for Rowhammer, but it wasn't clear. What's going on there?
So if you look at circuits, for the signal to be ready at the output, electrons have to travel a bit. If you increase the voltage, things will go faster. So you will have the output signal ready at an earlier point in time. Now, the frequency that you choose for your processor should be related to that. So if you choose the frequency too high, the outputs will not be ready at this circuit. And this is exactly what happens. If you reduce the voltage, the outputs are not ready yet for the next clock cycle.
And interestingly, we couldn't fault really short instructions. So anything like an add or an XOR, it was basically impossible to fault. So they had to be complex instructions that probably weren't finishing by the time the next clock tick arrived.
Yeah.
Thank you.
Thanks for the answer. Microphone number 4 again.
Hello, it's a very interesting theoretical approach, I think, but you were capable to break these crypto mechanisms, for example, because you could do zillions of iterations and you are sure to trigger the fault. But in practice, say someone is having a secure conversation, is it practical, even close to possible to break it with that?
It totally depends on your threat model. So what can you do with the enclave? We are assuming that we are running with root privileges here, and a root privileged attacker can certainly run the enclave with certain inputs again and again. If the enclave doesn't have any protection against replay, then certainly we can mount an attack like that. Yes.
Thank you.
Signal Angel, your question.
Somebody asked if the attack only applies to Intel or to AMD or other architectures as well.
Good question. I suspect right now there are people trying this attack on AMD in the same way that when Clockscrew came out, there were an awful lot of people starting to do stuff on Intel as well. We saw the Clockscrew attack on ARM with frequency. Then we saw ARM with voltage. Now we've seen Intel on Intel with voltage, and someone else has done similar. Voltpone has done something very similar to us, and I suspect AMD is the next one. I guess because it's not out there as much, we've tried to do them in the order of, scaring people. Scaring as many people as possible, as quickly as possible.
Thank you for the explanation. Microphone number 4.
Yep. Hi. Great. Thanks for a great presentation. Can you get similar results by hardware? I mean, by tweaking the voltage that you provide to the CPU? Or?
Well, I refer you to my earlier answer. I know for a fact that there are people doing this right now with physical hardware, seeing what they can do, yes. And I think it will not be long before that paper comes out.
Thank you.
Thanks. Microphone number 1, your question. Sorry. Microphone 4 again, sorry.
Hi, thanks for the talk. 2 small questions. One, why doesn't anything break inside SGX when you do these tricks? And second one, why when you write outside the enclave's memory, the value is not encrypted?
So the enclave is an encrypted area of memory. So when it points to an unencrypted, it's just going to write it to the unencrypted memory. Does that make sense?
From the enclave's perspective, none of the memory is encrypted. This is just transparent to the enclave. So if the enclave will write to another memory location, yes, it just won't be encrypted.
Yeah. And what's happening is we're getting flips in the registers, which is why I think we're not getting an integrity check, because the enclave is completely unaware that anything's even gone wrong. It's got a value in its memory, and it's going to use it.
Yeah. The integrity check is only on the memory that you load from RAM.
Thank you.
Okay, microphone number 7.
Yeah, thank you. Interesting work. I was wondering, you showed us the example of the code that wrote outside the enclave memory using simple pointer arithmetics. Have you been able to talk to Intel why this memory access actually happens? I mean, you showed us the output of the program, it crashes, but nevertheless it writes the result to the resulting memory address. So there must be something wrong, like the attack that happened 2 years ago at the Congress about, all that stuff.
So generally, enclaves can read and write any memory location in their host application. We have also published papers that basically argue that this might not be a good idea, good design decision, but that's the current design. And the reason is that this makes interaction with the enclave very easy. You can just place your payload somewhere in the memory, hand a pointer to the enclave, and the enclave can use the data from there, maybe copy it into the enclave memory if necessary, or directly work on the data. So that's why this memory access to the normal memory region is not illegal.
And if you want to know more, you can come and find Daniel afterwards.
Okay, thanks for the answer. Signal Angel, the question from the internet.
Yes, the question came up if how stable the system you're attacking with the hammering is while you're performing the attack.
It's really stable. Once I'd been through 3 months of crashing the computer, I got to a point where I had a really really good frequency voltage combination. And we did discover on all Intel chips it was different. So even what looked like, we bought almost an identical little NUC. We bought one with exactly the same spec, and it had a different sort of frequency voltage model. But once we'd done this sort of benchmarking, you could pretty much do any attack without it crashing at all.
Yeah. But without this benchmarking, it's true, we would often reboot.
It was a nightmare, yeah. I wish I'd done that at the beginning. It would have saved me so much time.
Thanks again for answering. Microphone number 4, your question.
Can Intel fix this with a microcode update?
So there are different approaches to this. Of course, the quick fix is to remove the access to the MSR, which is, of course, inconvenient because you can't undervolt your system anymore. So maybe you want to choose whether you want to use SGX or want to have a gaming computer where you undervolt the system or control the voltage from software. But is this a real fix? I don't know. I think there are more vectors, right?
Yeah. Well, I'll be interested to see what they're going to do with the next generation of chips.
Yeah.
All right. Microphone number 7, what's your question?
Yeah, similarly to the other question, is there a way you can prevent such attacks when writing code that runs in the secure enclave?
Well, no. That's the interesting thing. It's really hard to do because we weren't writing code with bugs. We were just writing normal pointer arithmetic, normal crypto. If anywhere in your code you're using a multiplication, it can be attacked.
Yeah, but of course you could use fault-resistant implementations inside the enclave. Whether that is a practical solution is yet to be determined.
You could write duplicate code and do comparison, things like that. But if, yeah.
Okay. Microphone number 3, what's your question?
Hi, I can't imagine Intel being very happy about this. And recently they were under fire for how they're handling coordinated disclosure. So can you summarize your experience?
They were really nice. They were really nice. Yes. We disclosed really early, like before we had all of the attacks.
We just had a POC at that point.
Yeah.
A simple POC, very simple.
They've been really nice. They wanted to know what we were doing. They wanted to see all our attacks. Yeah. I found them lovely.
Yes.
Am I allowed to say that?
I mean, they also have interest in making these processes smooth so that vulnerability researchers also report to them. Yeah. Because if everyone says, oh, this was awful, then they will also not get a lot of reports. But if they do their job well, and they did in our case, then of course, it's nice.
Okay, microphone number 4.
We even got a bug bounty.
We did get a bug bounty. Yeah. I didn't want to mention that because I haven't told my university yet.
Thank you for the funny talk. If I understood you right, it means to really be able to exploit this, you need to do some benchmarking on the machine that you want to exploit. Do you see a way to convert this to a remote exploit? I mean, that to me it seems you need physical access right now because you need to reboot the machine.
If you've done benchmarking on an identical machine, I don't think you would have to have physical access.
But you would have to make sure that it's really an identical machine.
Yeah.
But in the cloud, you will find a lot of identical machines.
Okay, microphone number 4 again.
Also, as we said, like the temperature plays an important role. You will also in the cloud find a lot of machines at similar temperatures.
And there's obviously stuff we didn't show you. We did start measuring the total amount of clock ticks it took to do maybe 10 RSA encryptions, and then we did start doing very specific timing attacks. But obviously, it's much easier to just do 10,000 of them and hope that one faults.
All right. Seems there are no further questions. Thank you very much for your talk, for your research, and for answering all the questions.
Thank you.
Thank you.